In this video, we're going to talk about a very important technique to use when studying equilibrium called ICE tables. There are some simple steps to follow. I'd like to go over those steps, and then as we tackle a couple of sample problems, perhaps the steps will become clearer in case they're not clear at first. So the first thing we'll do when solving an equilibrium problem is write expressions for the reaction quotient Q and for the equilibrium constant K. Next, we'll list out the initial concentrations. We'll calculate a value for the value for the reaction quotient Q, compare it to K to determine the directional shift, either left or right. Fourth, we'll define changes in terms of X. We won't know right off the bat how much of a substance is gained or lost, but we can define their ratios in terms of X, plus 2X, minus 1X, etc. And that'll be based on the coefficients from the balanced equation. 5, apply the changes to find the equilibrium conditions in terms of X. That is, we're going to fill out the last line of an ICE table. I'll show you what that means in a moment. And then lastly, substitute equilibrium concentrations into the equilibrium expression and solve for whatever the question asks. Sometimes they're going to ask for the value of the equilibrium constant and give you concentrations. Sometimes they're going to give you concentrations and ask for the value of the equilibrium constant. We just need to be prepared for whatever the question asks for. Let's try one together. In this case, we're going to be asked to find the value for the equilibrium constant, knowing one of the equilibrium concentrations. A 1-liter flask was filled with 2 moles of gaseous SO2 and 2 moles of gaseous NO2 and heated. Notice those are both of the reactants, SO2 and NO2. Initially, they don't mention the presence of either product. SO3 and NO, those are not mentioned at all. After equilibrium is reached, it was found that 1.3 moles of gaseous NO is present. From that information, calculate K. Let's start by writing the expression for the equilibrium, the reaction quotient Q. It's product concentrations multiplied together, all over reactant concentrations multiplied together. If there were coefficients other than the implied 1 that we find in this equation, we would raise these concentrations to an exponent equal to that coefficient. Furthermore, as you may recall, there's a non-mathematical subscript 0 written outside the brackets in this expression. That just means that we're dealing with initial concentrations. Now, since they didn't tell us about any SO3 or NO initially present, that means the SO3 and NO concentration is 0. They did tell us that there's 2 moles of SO2 in a 1-liter flask. So if you divide 2 moles by 1 liter, you get 2 molar. Same thing for the NO2, 2 moles in a 1-liter container gives us a 2 molar concentration. If the problem doesn't mention the SO3 being there, then it's not. You should assume that the concentration is 0. Same thing for the NO. Okay. Let's plug in what we have. 0 times 0 over 2 times 2. That'd be 0 over 4, which works out to be 0. Is Q greater than or less than K? Well, we weren't given a value for K. In fact, we're asked to calculate a value for K. But K is always going to be positive. And so if you've got a value for Q equal to 0, then Q is less than K. Now, what does that mean in terms of directional shift? We're going to shift right. We have to make more products. Okay. Now let's talk about what that means. Revisiting our bar graph from note set 2 in Unit 9. If Q is less than K, we need to shift right to reach equilibrium. That means our calculated ratio of product concentrations over reactant concentrations isn't high enough yet to be considered at equilibrium. If Q is equal to K, then your system is already at equilibrium, no shift needed. If Q is greater than K, the system's going to shift left, make more reactants, because Q is already, the ratio of products over reactants is already higher than that required for the equilibrium. And last possibility is Q less than K, the system will shift right, make more products to reach equilibrium. That's the situation we have here. We've determined that Q is 0, and even though we don't know the value for K, it's going to be above 0. So Q is less than K. We need to make more products, make more of the substances on the right side of the reaction arrow in order to reach equilibrium. Okay, so let's write out that equation. SO2 and NO2 yields SO3 and NO. Our initial concentrations were 2, 2, 0, and 0. We're going to define the changes in terms of X. Now, we had just established that we shift right, make more of the substances on the right side of the arrow. Hence, plus X for the SO3 and plus X for the NO, minus X for the SO2, minus X for the NO2. We don't know how much, but we know that the SO2 and NO2 concentrations during the course of reaching equilibrium will have to go down, and the concentrations of the SO3 and NO will have to go up because we're shifting right. Lastly, we're going to apply the third line of an ice table. See how this spells out ice, initial change in equilibrium. And to get that equilibrium line, we're simply going to add together what we had initially, 2, and the change, minus X. We can't simplify that, but we can put it all together in one expression, 2 minus X. Same thing for the NO2, 2 minus X. Can't simplify it, but we'll write it as one expression, 2 minus X. For the SO3 and the NO, it's 0 plus X. Well, that's equal to X. At equilibrium, we were given the concentration of NO. It was 1.3 molar. Now look at your ice table. Under NO at equilibrium, the concentration of NO is X. And we know the numerical value for that. It's 1.3. So X is equal to 1.3. It must be. Once we know that, we can substitute in to the equilibrium constant expression K. If we know that X and X are the concentrations of SO3 and NO, and we know that the expressions 2 minus X and 2 minus X are the concentrations of NO2 and SO2, then we're simply going to substitute 1.3 wherever you see X. So 1.3 and 1.3, instead of writing 2 minus X, we'll write 2 minus 1.3. Take out your calculator now. 2 minus 1.3, that's 0.7. And you have to multiply that by another expression, 2 minus 1.3 or 0.7. Crunching the numbers, we arrive at a value for K of 3.45. Woofda, that was a big one. Let's try one more sample problem. Here's one where I'm going to ask you to calculate equilibrium concentrations knowing the value for K. Here's a balanced equation. H2 and I2 yields 2HI. A mixture of 0.5 moles of H2 and 0.5 moles of I2 was placed in a 1 liter stainless steel flask. Calculate the concentrations of all species at equilibrium, and they give you the value for K, 54.3. Let's start by writing the expression for Q. Product concentrations raised to the power of its coefficient. Notice that there's a squared term there. That's a non-mathematical subscript 0 outside the brackets. The two reactants, H2 and I2, they don't have coefficients in the balanced equation, but we do know their numerical values. It's 0.5 moles in a 1 liter flask. So 0.5 over 1, 0.5 over 1. If they don't mention the HI initially present, then it's not there. Its concentration is 0. Students, it will often be the case that a chemist prepares a reaction with nothing but reactants in the vessel, and the products he or she figures will be formed during the course of the reaction. So if we plug in what we've got, 0 squared over 0.5 times 0.5, that equals 0. We know that the value for K is 54.3. So if we make the comparison between Q and K in this case, we can see that Q is less than K, which means that we need to shift right, make more products in order to reach equilibrium. Okay, what does that mean for us? Well, we're going to write the balanced equation and prepare an ice table. And I draw your attention to the coefficient 2 in front of HI, because that's going to play an important role here. The initial concentrations of H2 and I2 were 0.5. The HI was 0 because it wasn't mentioned. We know that we're shifting right. That means we're going to put a plus underneath all of the products. There's only one product in this case, but if there were more than one, I'd put pluses under them. And then the reason we put minuses under the reactant is because in order to make products, necessarily you're using up reactants. There's no other way to make products than to use up reactants. So that's why there's a minus in front of or underneath the H2 and the I2. Also, please notice, unlike the previous sample problem, we have a coefficient in front of the X. That coefficient 2 is reflective of the coefficient in the balanced equation, HI, for HI. It's a 2. Notice that the implied 1 in front of I2 is also the implied 1 in front of X, and the implied 1 in front of H2 is also the implied 1 in front of X. To flesh out the ice table, the equilibrium line, simply add together what you've got in the initial and the change, and you write it as one expression, 0.5 minus X. 0 plus 2X, for HI, that's 2X. Okay, the equilibrium constant, HI squared over H2 times I2. Well, we know that 2X is the concentration of HI. Let's plug that in. We know that the expression 0.5 minus X is the concentration for both H2 and I2. And we know that the numerical value for K, which was given to us, is 54.3. Okay, now it gets a little bit, there's a little bit of math here. Notice that if in the denominator of the expression you have 0.5 minus X times another 0.5 minus X, that's the same as 0.5 minus X squared. We have a situation called a perfect square, which means something squared in the numerator and something squared in the denominator. Take the square root. If you root both sides, we'll have the root of 54.3 and the root of the expression 2X quantity squared over 0.5 minus X quantity squared. The root of 54.3 works out to be 7.36. And on the right side of the equation, it's greatly simplified. This becomes a simple algebra problem. 2X over 0.5 minus X. We'll multiply both sides by 0.5 minus X. Distribute the 7.36 through the parentheses. We get 3.68 minus 7.36. X equals 2X. Add 7.36X to both sides. We get 3.68 equals 9.36X. Divide both sides by 9.36. And we get a numerical value for X of 0.393. Now, you might say, are we done yet? Not quite, not quite. We're almost there. We now have a numerical value for X. In the equilibrium line of the ice table from above, we have expressions for each equilibrium concentration in terms of X. All we need to do now is plug in X and solve for each one. So in the case of H2, 0.5 minus X, that would be 0.5 minus 0.393. That works out to be 0.107. The same is true for I2. I2, 0.5 minus X, that's 0.5 minus 0.393, which works out to be 0.107 molar. And then lastly, HI, 2 times X, that's 2 times 0.393. That works out to be 0.786. We now have solved for the equilibrium concentration of all species at equilibrium, and we've shown work all the way through. Good work, students, and good luck on the homework.